right? But what we're saying here is this function definition says, if you give me some nat, I will give you a new nat, right? If you give me some inhabitant of this type, or some proof of this proposition, although nat itself isn't a proposition, I will give you a new inhabitant of that type, right? So implication is just function abstraction, right? It shows you how, given an evidence of something, I can build an evidence of something else. And of course, just as we can compute with this evidence, right? So what happens under the hood if I evaluate add 1 applied to 2, right? It's going to take a concrete inhabitant, the concrete inhabitant 2, and it's actually going to produce a new number 3, right? It'll construct that data type of type nat. In a similar way, when we partially apply proofs to some other piece of evidence, it's actually building up, in theory, under the hood, it would actually build up a complete proof term where we filled in all occurrences of that assumption with the argument, that the evidence that you supplied to it. But because proofs aren't computationally relevant, it doesn't actually build these terms under the hood. It doesn't have to, because you're never going to do anything interesting with them. It's just sort of manipulating evidence around. So, okay, oh right, this is actually really, really key. So you've noticed, well, you've probably noticed that in all of our proofs, when we write a theorem or a lemma, we always terminate the proof script with QED, right? And this actually has a very specific meaning in coq. It tells the proof checker, or coq itself, that the term you're constructed can be treated as opaque. And you never actually have to unfold this definition or do anything with the proof term you built under the hood. So this, why do we do this? It's because these proof terms can actually be quite complex and gross. And if we actually did try and compute with them, we would build up these massive terms and it would be quite slow. And we never actually want to do that. So QED says, oh, don't worry about that. But if we're actually building up a function like add in here, like we do with add in here, and we want to actually compute with it and evaluate it and actually inspect the term that we built up, you need to use this special defined identifier. And this says, okay, take the term that you've built up and actually make it so I can unfold it and use that definition later on. So if we hit QED here, so here's the key difference. So I used QED instead of define at the end of this definition command. And now when I compute add 1, 2, note that it didn't actually unfold this definition or compute with it anyway. It just sort of left that opaque. It didn't unfold the definition. Because, again, we don't actually care about what these proof terms actually look like. So the key bit here is if you ever use tactics to define a function, which actually can be quite useful if we're using defining very dependently typed functions, and you'll probably see many examples of that later in the week. Use defined at the end instead of QED, or else you won't be able to do anything interesting with it. You won't actually be able to compute with it. Right. And with that, maybe I'll just answer more questions as necessary about this Curry-Howard isomorphism correspondence. I encourage everyone to, at some point, go and actually look at this optional proof objects chapter and walk through the exercises and the examples. Maybe after you've done some more regular programming exercises. And it can be a very eye-opening experience for what's actually going on under the hood in coq. And proving in general. Yeah, one last.
More of an Emacs question. Is there a way to make the show proof persistent? Do you know?
I don't off the top of my head know if there's some default way to do that. No, I don't. And I will say that generally speaking, you won't want to do that because these proof objects can get, just for kicks and giggles, let's see what the proof object built up for this looks like, for this filter not empty n.